All right, if everyone can have a seat, we're going to go ahead and get started. All right, thank you all so much for joining for our August meetup for the Bay Area Research in Natural Language Processing and Machine Learning group. Just as a little bit more info about the group, if this is your first meetup, there are a lot of meetups out there for NLP and ML, and our real focus here is on research and new approaches in machine learning and natural language processing. So what you'll typically hear at our meetups is sort of novel approaches that we've come up with in-house or that other speakers that we bring in from other companies or universities have been experimenting with. Could be related to a paper they've recently published. So that's kind of what the meetup group is about. Just to tell you a little bit more about Maya, I'm sure you saw the gigantic logo on the back wall. So Maya Systems is a company an AI recruitment company that brings together deep learning and NLP expertise to support the end-to-end recruiting process. And we have a virtual assistant that is also named Maya, who interacts with job candidates throughout that process. And we are hiring, so if you're interested in learning more, Lauren, who is our head of recruitment, would be happy to talk to you about job openings that we have available right now. So as I do every meetup, those of you who are veterans are going to know what I'm about to say. If you could actually take out your phones for the only time I'm going to suggest this for the talk, and go look at the date and time on this meetup, which is our next month meetup. It's our September meetup. Add it to your calendar. Make sure you come join us. We'd love to have you back. We're going to be having Amir Kargar, a machine learning engineer here at Maya, talking about natural language inference. I'm really looking forward to that talk as well. So please feel free to put that in your phone, and then you can store your phone and put it on silent for the talk. As with all of our meetups, we have a link on the page for if anyone who's attended a meetup would like to submit an idea to speak at a future meetup. We really, really encourage that. It's not a requirement that you have published the work that you'd be presenting in any kind of journal or anything. It could just be some kind of experimental work that you will be sort of working on that you'd be interested in presenting in front of a crowd that is sort of knowledgeable on the topic. So please do submit. It's just a Google form with a few questions about the idea that you would want to present. So that would be great. Just as a little house clearing item. So we have the key for the restroom in the back corner near the door. The men's restroom is out of order, but we do have one key that you can use for the women's restroom. So everyone is welcome to use the women's restroom, and it's just a one-at-a-time use. So without further ado, I'm going to go ahead and introduce Andy. So I'm going to read just like a little brief bio to give you guys a background on Andy. So Andy is an AI engineer here at Maya Systems, where he's been focused on reinforcement learning and language acquisition. Previously, he's worked in the healthcare domain, where he built the first system to extract follow-up recommendations from radiology reports and notify physicians of missed exams. He has also worked in defense contracting, where he did research and development in social network analysis, but he swears he never influenced a single election ever. And just a little bit more info about his talk. Andy will be discussing new approaches in NLP that use reinforcement learning to push state-of-the-art performance across a number of language tasks. Andy will discuss how summarization, machine learning, image and video captioning have all benefited from inclusion of reinforcement learning. And Andy will also discuss how reinforcement learning is used in new ways to rethink language learning itself in multi-agent systems and grounded learning environments. He will explore these cases to see how reinforcement learning can be used today to improve model performance, as well as to consider open questions in research. If you do have questions, we'd ask that you save those to the end of the presentation. So without further ado, I'd like to welcome Andy Mullenix.
Cool. So thank you, Zach, for the intro, and thank you, all of you, for coming out tonight. The meetup keeps growing every month, which is really exciting. So glad you found this topic interesting and took the time to come out. So yeah, I thought it would be fun to do a talk on reinforcement learning and natural language processing, and why you might choose to do such a thing in the first place, and what the pros and cons are if you do that. there's a lot of material to cover, so my plan to try to get us there is to begin by attempting to motivate the use of reinforcement learning in natural language processing. Having hopefully established that motivation, we'll then take a moment to do a quick review or overview of the basics of reinforcement learning for anyone who's not familiar or could just use a refresher. After that, we'll dive deeper into what it really looks like to use rewards rather than labels during training. And if you're using reinforcement learning, that's essentially what you're doing. You're using rewards. We'll wrap up that part of the talk by discussing some of the challenges that you'd face if you're working with rewards like that. And at that point, I'll transition to a somewhat different topic on reinforcement learning and grounded language learning, which is definitely like way more on the basic science end of the research spectrum, but I think a really interesting topic for trying to get us to true language understanding in the end, which is obviously a very subjective and biased opinion. But anyway, why turn to reinforcement learning in the context of natural language processing? To answer this question, I'd like to first narrow the scope a little bit and focus primarily on text generation, which hopefully isn't too disappointing. It might sound limiting at first, but it actually encompasses a lot of the tasks that we deal with in NLP, like machine translation, abstractive text summarization, dialogue training, image and video captioning, and things like that. So we'll be looking at the now familiar encoder decoder framework, where some input, in this case a text, is processed in its entirety by an encoder module, which distills that input into some context vector or set of vectors, which is then fed into a separate decoder module, which then is tasked with generating the output text one word at a time. In this case, this is what it would look like if you were trying to train a system to learn the comedy of BJ Novak. But we don't actually care what the input on the left is. It could just as well be an image. Doesn't really matter what caption you give Success Kid, because he's always funny just by himself. So we'll essentially just look at the left side of this as a black box, and really the encoder should be a black box as well. We'll be focused on the right side. So obviously this is trained normally through supervision with a cross-entropy loss, with input-output examples. That's been around for a while, this encoder-decoder framework. It's tried and true, so what could possibly go wrong? It turns out a lot of problems actually surface at test time when you train this way. A very common one, you'll see this in a lot of papers, is unwanted repeats, where the model was supposed to output, I'm not myself, you see, but instead it just kept repeating you see over and over again. So it hasn't learned when to stop generating text. Somewhat annoyingly, it also has the exact opposite problem. Sometimes it doesn't know when to continue, and it'll output just fragments of what the full text should be. In this case, it can make sense, but sometimes it doesn't. It could be an incomplete clause or something like that. And finally, they tend to produce really boring text a lot of the time. They're sort of like placeholder texts, like I don't know and yes and no and things like that. This happens particularly if your training set has a lot of samples where the input is different, but the output is the same. That can happen with things like I don't know. So these are just some of the issues that surface during evaluation of models trained with cross-entropy. And why do they occur? Well, when we do train them, we actually use a technique called teacher forcing, where some input, in this case Homer Simpson, an image of Homer Simpson eating a pink donut, is run through some encoder that's distilled into some context, which is used to initialize the decoder on the right, which is what we're actually interested in. That decoder receives some special start of sentence token, and from that point on is supposed to do an argmax at each step, making a word prediction. But it doesn't actually matter what it predicts. As far as what it sees, it's going to observe that ground truth sentence at the bottom, no matter what it outputs. That sentence, Homer is eating a pink donut. We do this because it offers some advantages to not doing it. The final accuracy of the model is typically higher if you use teacher forcing. Learning is more stable, it's faster, things like that. But it has some drawbacks, at least combined with supervision. The first one is exposure bias. It's only ever seen the correct sentence. It hasn't during training, been exposed to its own predictions, which at test time are inevitably going to contain some errors, which can easily compound over time and throw the whole sentence off the rails. And then the second thing I'd like to talk about is that tuning these models is ad hoc. And what I mean by that is, say you would like to prioritize the elimination of repeats, like we saw earlier, or maybe you would like to prioritize diversity in the generated sentences. It's not intuitive. It's not really immediately obvious where to work that into the training regime. I've seen approaches to that problem that actually modify the beam search at the end, which is essentially just using engineering to overcome the limitations of machine learning. And we would like to instead try to take care of those things during the learning process itself. I'll not present mode. Sorry about that. And so the last one is that, and this is most subjective, but I think most interesting or most pertinent for the talk. Different metrics are used for training and testing. So during training, we use cross entropy, right, and then backpropagation. But during testing, what do we actually use? We use metrics like BLUE and Rouge and CIDR, and ultimately human evaluation. These are totally different from how we train them, the models, and they all happen to be non-differentiable, which thankfully is not a problem for reinforcement learning. So all of this led to a question a year or so ago, probably a couple of years ago. What if we just optimize directly for the criteria that we actually care about? So what if instead of training using cross-entropy on input-output examples, we just optimize using, say, CIDR or Rouge or something like that? That's in the process of doing this, we hope to eliminate exposure bias and hopefully gain tunability. This is really the main idea of the first part of the talk, is this like harmonizing, I guess, or unifying training and testing and the metrics that we use during each of those processes. And so the way we'll do that is, of course, with reinforcement learning, and we'll cast the text generation problem as an action-taking problem in a reinforcement learning setting. So it's a good time to do a quick review of reinforcement learning for any who would like to review. This is really the canonical diagram for the reinforcement learning setting. You'll see this in any introductory text. I think this one's from Button and Sarto. Basically, you have an agent and an environment. And if you start at the very beginning of time, the environment produces some state. And the agent observes that state, makes some decision using it, produces an action. And that action is then output, fed back into the environment, which can then update the world state if the action indicates that it should. And then it outputs the next state of the environment. And optionally, a reward if the agent happens to have done something good. This goes just in a loop over and over again. In practice, we're interested in finite episodes, so we might have with discrete time steps. So we might have, say, an episode of 20 time steps, where each step in the episode is in a loop of this diagram. Typically, the reward is sparse. It doesn't get a reward every time step. And in fact, it's pretty common for an agent to get a reward only at the very end of an episode. For a sentence, that might not be so bad. For a video game, it can be something like 10,000 steps. And then it finally gets a reward and has to figure out the task then is to perform credit assignment, to figure out which of its actions were good and led to the reward. Similarly, if it gets a negative reward, then it needs to figure out which of its actions were bad and should be avoided in the future. So, sorry to throw math at you in a presentation, but some of the fundamentals for reinforcement learning are basically we're going to be looking at policy gradient methods, which is just one branch of reinforcement learning, but it's what's relevant to the methods we'll be looking at today. So a policy, pi, parameterized by theta, is just a function that takes a state and an action and then outputs a probability of the action. Another way to frame this, probably more common and maybe more useful, is that policy just receives the state, not the action, and then it outputs the entire distribution over all of the actions, so a probability distribution. And then the objective, J, is the expected reward of the entire episode. This is what we're going to try to maximize. We want to get as much reward per episode as possible. And then the value function, v, is just a function that takes a state and returns the expected reward from this point in time all the way to the end of the episode. We don't care about any reward that we received before the state s, just from state on, how much reward do we expect to get. And similarly, the action value function is the same thing, but for a state and action pair. So I'm in this state, I perform this action, what's the value of doing that? Combining all of these, we get a fundamental result in RL, which is the policy gradient theorem, the equation at the bottom. This is from David Silver's excellent UCL course on the topic, where it basically just says the gradient of the objective function is the expectation of the gradient of the logarithm of the policy times the action value function. This is an exact analytical result, but during training, we actually will typically approximate Q over here. And speaking of training, this is how we train it with the well-known reinforce algorithm. It's pretty simple. Basically, we just initialize the policy at the beginning of time, and then we sample an entire episode from beginning to end. Each step of the episode will yield a triplet of a state, an action, and a reward. The reward might be 0, but it's still something. And so we have a set of these triplets all in a row. We collect the whole thing, and then we step through them one after another, performing an approximate update modeled after the policy gradient theorem. But the VT in this case, it's poorly named. It's not actually the value function. Instead, it's the return, which is the actual observed reward from this point in time on to the end of the episode. The value function is an expectation. This is an actual value that we observed. And that really gives the reinforced algorithm its properties of convergence. It has pretty good convergence properties. It's very likely to converge, but it's slow to converge. And that's because this return that it uses here has no bias. It came from a sample, but it has high variance. And that high variance makes it hard for to make sense of the signal that it's getting if the reward is all over the place. So one of the ways to deal with that is with a baseline. That's what we'll be looking at, where this equation at the bottom, which is also a restatement of the advantage function, if you've heard of that. Basically, we take the same return, and then we subtract from that some baseline function. In this case, it's the state value function. That turns out to be a good baseline a lot of the time, but it doesn't have to be that. What makes something a good baseline is if it just effectively reduces the variance of that reward over time. So how do we do this for text generation? Like I said, we want to cast text generation as an action-taking problem in reinforcement learning. We do that by basically sampling from some input distribution still. We still have training data. We process the entire input with the encoder and distill that into some context. That's used to initialize a decoder as well as some start of sentence token. At that point, we begin the episode. So all of the steps of the decoder constitute the episode of the reinforcement learning environment. This is a little bit of what that looks like, and it's not much dissimilar to the example with Homer Simpson, except the way in which we're getting the token and what we do with it. We're not taking an argmax over the distribution, and we're not providing a ground truth. Instead, we're sampling from a distribution, and we're actually using that as the input at the next step. It means first of all, it's exploratory in nature. Since we're sampling, it won't always be the highest probability token that gets sampled. And the agent is exposed to its own output noise during training. This is the simplest way to do it, but it's a little unstable and slow to train, much like how in the supervised case, if we eliminate a teacher forcing, we have issues of slowness and instability. The same thing happens here. Only in this case, we know why it's happening. It's easy because we have no baseline. We just need to reduce the variance of the training. So this takes us to what I think is a really fundamental paper in this topic called self-critical sequence training for image captioning. Their technique works really well. It's used a lot by some leading research think tanks. I know Salesforce has put out a series of abstractive summarization papers using reinforcement learning. And this is the exact method they use. They cite this paper. Basically, they reduce the variance by taking the output of the same model at test time inference to baseline the rewards that is experienced by the model during training. So now, for each step of the reinforce algorithm, we're actually generating 2 sentences. One through sampling, that's the first reward here, the reward WS. And then we subtract from that a baseline version of sampled sentence, which is generated using argmax. So it's acting, same policy, acting greedily. Reduces the variance over time. This works quite well, and it also has the nice effect of that the only samples that outperform the current test time system are given positive weight, and inferior samples are suppressed. This is what it looks like in the diagram. At the top, we see the normal sampling procedure, and then at the bottom, we see it acting greedily with argmax. So we get 2 generated sentences. We compute a score for each of them using one of our metrics, in this case, cider rather than blue. We reduce those to scalars, we subtract them, and then we plug them back into the policy gradient theorem for the update step. This works pretty well. At the time of publication last year, it pretty much annihilated the state of the art on MS Cocoa, and conveniently optimizing directly for cider also improved performance on all of the other metrics. But I think the most interesting result that they found was when they evaluated trained models on a really fun data set called objects out of context, which is pretty self-descriptive. The strengths of the reinforcement learning method really shined. At the bottom, we see the same model trained in 2 methods, one in cross-entropy and supervision, one with SCST. There are 5 outputs because I think they do a beam search at the end of the process. The best example that the cross-entropy method came up with, it gets pretty confused pretty early. It says a blue of a building with a blue umbrella on it. The SCST method is able to generate a caption that makes sense, which is a blue boat is sitting on the side of a building. So why does this happen? I mean, when you see something out of context, the generated sentence is typically going to be something unusual by default, right? So if a model was trained only ever seeing the ground truth, then it's never even seen its own errors, let alone something crazy like a ship on the side of the building. But if you train with reinforcement learning, instead, you get this robustness to noise because it's been exposed to all sorts of its own absurd sentences during training. So that's pretty cool. We now have a reliable method of training text generators, using the metrics that we care about, or at least that we care about during this talk. So what else can we use as a reward? Can we wait just until the end if you don't mind? Thanks. It's an interesting question, or a worthwhile question to ask, because rewards are very tunable. They're composable. They're just some functions. We can write them. If you can think of a way to convert something into a reward, then you can try to shape your agent's behavior that way. So this is, I think, a paper that is a really fun example of showing how far you can go with this idea and doing unexpected things called reinforced video captioning with entailment rewards. They start with the observation, well, first of all, they're optimizing for cider, which is an n-gram-based metric. They start with the observation that n-gram matching doesn't really capture a lot of the nuances of language, like negation and having the wrong action or object in a sentence. An example of that is a person is playing football and a person is playing basketball. We'll both get a high cider score together, but they're really describing different events. So they deal with that by using a pre-trained textual entailment classifier to determine if a candidate's sentence is actually entailed by one of the referenced sentences. I think this is a pretty novel approach. For anyone who's not familiar with entailment or well familiar with it, here's an example. Basically, we want to know if the second sentence is entailed by the first sentence. The first one is a soccer game with multiple people playing. And then the second sentence is some people are playing a sport. We would say in that case that the second sentence is entailed by the first sentence. It's getting at a shared meaning. It's not that their meaning is the exact same, but they have some overlap in their meaning. And so they use this to basically complement the cider reward. So it looks like this. By default, we just use the cider reward. But if the entailment classifier yields a low enough score for the generated sentence, that is, it's not entailed by the reference sentences, then we essentially punish the agent for having generated a sentence that isn't entailed. A quick example of where that comes in handy is, again, this is for video captioning. So we have a few frames from a video. The ground truth, it's basically a band, a rock band playing at a concert. And the ground truth captions are a band is performing a song. and a rock concert performed by a band. Then we take the same model, train it 3 different ways: cross entropy, RL without an entailment classifier, and then RL with an entailment classifier. So the cross entropy method, makes an understandable mistake, saying a person is playing a video game. It doesn't kind of look like a video game if you glance at it. The pure RL gets a little closer with the band is playing a video game, but it doesn't have any kind of entailment indicator, so it doesn't know that it's using, it doesn't have a good signal to know that it's using like the wrong object of the action. And then, when we include entailment, sorry about that, entailment into the equation, it's able to then get the right object because it knows that this is describing the same a sentence that's entailed by the reference sentences. So that's pretty cool because we're now able to reuse a lot of the work that's already been done by the NLP community over years, decades. I mean, all these data sets that have been produced meticulously and all the refinement on models and everything can now be reused in pretty novel, unexpected ways to do things that we couldn't really do before. So just some ideas I want to throw out there of what else you could do with this would be like the same idea of entailment, but instead of using cider, use negative of cider or some other difference metric so that you could generate sentences that mean the same thing as the input sentence, but use different words. You can also use pretty much any sentence classifier. You can think of like sentiment or tense. Again, you could input one sentence and then train a model to convert that into a sentence with a different sentiment. This would be very similar to what's been done with like conditional variational autoencoders on controllable text generation, but using reinforcement learning instead of autoencoders. The 3 at the bottom I'm not intimately familiar with, but I've seen them done, and I'll include them in the citations at the end of the paper. People have created measures of informativeness, of coherence, of keyword retrieval confidence. It's kind of the sky's the limit. It really depends on what your domain is and what your imagination is, if you could conceive of a reward function for your problem set. So I talked a little about the disadvantage or challenges of the cross entropy method, so it's only fair that I do the same for RL. I'd like to quickly highlight some of the 3 challenges you might encounter with this approach. This is an analysis done by the last paper we just talked about, the reinforced video captioning with entailment. They basically they crowdsourced some workers, like Mechanical Turk, provided them with 2 sentences. One is a reference sentence, and then another is a generated sentence. And then they're asked, is the second sentence relevant to the first one, and is it coherent? Is it readable? So the results are kind of interesting when they compare the cross entropy, training through cross entropy versus RL with no entailment. We see that it does better with relevance, but slightly worse with coherence. And then when we further compare RL with entailment to just plain RL, we see further improvement on relevance, which makes a lot of sense. That's what we're optimizing, but still poor coherence versus the supervised method. So this really confirms a problem that many of you are probably wondering about throughout the rest of the first part of the talk, which is if we're optimizing for these metrics, aren't the agents just going to game the metrics? And yeah, they do. So that makes sense. I'll see if this plays here. This is a video from OpenAI that shows how hard it can be to get rewards right. I'll just let this speak for itself for a moment. It's supposed to be a race. So it gets stuck here. So if you try to get it to not just win a race, but also get as many points as it can along the way, that can very easily go wrong. Instead, it's just found a local optimum for just getting the most points that it can, just getting these gems over and over again, while everybody else is actually trying to win the race. So it can be tricky. It's a case of be careful what you wish for with reward design. This happens a lot. It's pretty challenging. And then finally, we have a well-known problem in reinforcement learning, which is sample complexity. Trying to teach a model language starting from scratch is a little bit like just guessing English. If you don't have any frame of reference, then the model is, like we saw earlier, just sampling from a distribution. So it's essentially guessing. It has to stumble upon a right word in the target sentence before it gets any kind of positive reward. So you have a lot of this type of situation where it just keeps getting wrong, and the reward loses its signal. This happens in lots of domains for RL, but because of these 3 challenges, that's why in practice people are actually combining the 2 approaches, supervised learning and reinforcement learning. And I think the methodology that is most effective for that is using a curriculum where you start off favoring supervised learning. You might use supervised learning for all but the last word of a sentence, and then use reinforcement learning on just the last word of the sentence. And then once you reach a certain reward threshold with that, then you back off a little more and you start training the last 2 words with reinforcement learning until you get back to the beginning of the sentence. This has the advantages of both systems. You get more readability from supervised learning. You definitely reduce the sample complexity. It gets the model in the ballpark so that you can avoid this problem. But you also get the robustness of the reinforcement approach. So that's all I'll say on the first part of the talk for the time being, but I'm happy to come back and talk or answer any questions at the end of the talk. For now, I'd like to transition to grounded language learning. So I'll start with a quote from Igor Mordich at OpenAI, which is, "An agent possesses an understanding of language when it can use language to accomplish goals in its environment." It's totally subjective, but I think it really captures the idea of grounded language learning. Sorry, did everybody get a chance to? Cool. Okay, so really what we're trying to do here is design environments, models, and learning procedures that allow models to overcome the same challenges that children face when they're acquiring their first words. So what are those challenges? They have to first induce structure in a continuous stream of visual input. They have to reconcile that structure with linguistic observations to associate words with objects and things like that. They have to store this knowledge in memory and apply it to inform decisions about how to best respond to situations in the future. So I'll be looking mostly at this one paper, Understanding Grounded Language Learning Agents, from Felix Hill at DeepMind. It's an interesting paper because they aren't really trying to beat any state of the art. They actually use a simple model. But they're trying to, it's really an analytical paper. They're just trying to poke and prod these models and under different experimental setups to see how grounded language is acquired and where it struggles and where it does well. This paper was recently rejected at ICLR under the justification that the grounded language agents are currently so bad it doesn't really matter. We're not really ready to ask these questions, but I think asking these questions is how we'll get better at grounded language learning in the first place. So they do this, they basically do this analysis by borrowing tests from neuroscience and psychology, which allows them to better isolate the learning behavior of the agents, and we'll see soon. So it looks a little like this. On the right, we have just a single observation, one frame from a video, and we have one word input, in this case chair, in the upper left. We see 2 objects in the room. One is an actual chair, and one is a confounding object. I think is a refrigerator here. So the goal in this case might be for the agent to learn what chair is and to identify that. It indicates that it knows what a chair is by moving toward it and occupying the same space. So it has to take action in a simulated world in order to indicate understanding. The model, like I said, is pretty simple. On the left, we process the visual input with a convolutional module and then the textual input with an LSTM. We combine them all in a mixing module, which is just a multi-layer perceptron. Then we output that to an LSTM. It's recurrent at the end because we want the agent's actions to have some sort of state so it can keep track of what it's done. So they conduct several tests. It might get a little tedious here, so I'm going to try to well, not let that happen, but I'll try to highlight some of the findings that were most interesting from this paper. First of all, shape color bias. It turns out infants have a shape bias. When they hear a new word that they've never been exposed to, they're more likely to think that it describes a shape. So they wanted to see if the same thing occurs with this model. So how do they do that? Well, they expose a model to some training words. Those words can be shapes, colors, or nonsense words like DAX, which in this case corresponds to black pencil. DAX isn't a real word, but the agent does observe it during training, and when it does, it always correlates with that atomic object, the black pencil. That has 2 properties, a color and a shape, which is noteworthy. So how do we conduct an experiment? Periodically throughout training, we do test episodes. Those constitute the experiments. During an experiment, the agent is shown a word, a nonsense word. DAX, which means black pencil. It's also showed two objects, one of which is a blue pencil and another is a black fork. So each of them has one of the properties of DAX, and the agent has to decide, does DAX refer more to color or to shape? Is it biased more towards one or the other? It turns out the convolutional neural networks have the opposite bias of what we observe in infants. Starting on the graph on the right, the blue curve is really what we're interested in because it indicates the test time behavior. If the curve is above the horizontal axis, then it indicates a shape bias. If it's below, it indicates a color bias. We see when we train only on shape words, as expected, when presented with an unknown word, the agent has more likely to assume that the word describes a shape. But we see an even stronger bias over on the far left if trained on only color words. And then if it's trained on an equal amount of shape and color terms, it still shows a color bias, which is really interesting. First of all, they conclude from this that convolutional neural networks actually have a bias towards shape or a color representation versus shape. I'm not sure if this finding is strong enough to support that conclusion, but it certainly indicates it. But I find this really interesting because it shows how using symbol grounding as an experimental framework can provide insights into modules that we use all the time in different settings, but we might not have known this property about convolutional modules if we hadn't tested them by forcing an agent to form correlations between different types of inputs as well as actions. So that was the first analysis, the study. The second study is on curriculum learning. We want to know if exposing the agent to all words at once during training is better or worse than exposing the agent to first a limited set of words and then increasing the number of words over time, only as it does better on the words that it's seen. So they have these two experiments that they run, one with all 40 words and then one with 2, then 5, then 10, then 40. And the results are pretty striking, especially on the graph on the right, where the vertical axis is words learned at a given time, which is measured during test time. The blue curve is the curriculum model trained with curriculum, and the red is the one trained without. Even though the model is only seeing a limited set of words until it gets to the full 40, it's still true that at every step of the way, the model has a mastery of more words at any given time than the other models. So we see a pretty strong conclusion or support for the benefit of curriculum learning. This is with just one word, so it might not hold for more complicated compound words or phrases or clauses. More analysis would need to be done for that. Another thing they look at is word learning speed. Of all these different types of words for shape, color, pattern, size, shade, and category, like furniture, is an agent better able to learn, does an agent learn one of these faster? Is it inherently biased towards understanding one of these more than the other? So again, they do two experiments. One is a controlled experiment where for each of those classes there are just 2 exemplars. And then one is what they call a naturalistic experiment where they have each of those classes has a different number of examples. I'll just cut to the chase on this. The case where it has more, which is shape, it has 40 shape words and only 12 color words. It manages to learn all 40 shape words before it acquires the 12 color words. So we see on the left that there's not really a strong bias towards learning anything except that patterns are a little harder to acquire in general if it only has one of each. But if you have more shapes than colors, then it's able to learn all the shapes before it can learn all the colors, even though before we found a color bias, which indicates that just having more examples of a class actually speeds up learning for that type of thing, which is a pretty interesting finding, I think. Last one I'll cover, because I think it's the most important, is negation. How do models learn to handle negation? So again, we have 2 different kinds of training words. One is shapes, one is colors. Say we have 12 training words. We divide that set into 2. Half of them will provide positive and negative examples for, like ball and not ball, and half of them will only provide positive examples for. And then during test time, if we show one of the in the second half with a negation, is it able to understand what it means to negate something that it's only seen positive examples of so far? For experiment 1, if they train on just 12 color terms evenly divided, there's only a 50% chance of being able to do that generalization. But if they add in all 40 shape terms along with the 12 color terms, then the chance goes up to 75%. So the takeaway from this is that with only one object class, like shape or color, the agent appears to simply, well, they actually provide some analysis for this, appears to simply memorize all objects that are not W. So if it's only saying colors, it can just memorize all the colors that aren't the one that it's negating. That doesn't generalize well. So you need more than one type of class in order for it to learn the concept of negation, what it actually means to identify and avoid something, W. That was kind of cool because there's a direct implication, something that could actually affect products today, which is that building some sort of negation-focused inductive bias in your models may actually be beneficial in environments with limited object classes, depending on what kind of problem you're trying to solve. So some closing thoughts on all of this. What do we get from reinforcement learning? In either case, we got early on with text generation, we got robustness to noise and tunability, which enable models to deal with unexpected images and the output that they produce in that case. And in general, well, definitely tunability. We could then shape that behavior however we wanted it, or for the most part. And then in general, we get active perception, which means that what the agent perceives is affected by its own actions. So in the case of grounded language learning, this really allows us to correlate vision, language, and action to try to understand all of them better individually and take them together. So in the coming weeks, I just want to say we'll release slides with all the citations probably tomorrow, and then I'll release a follow-up blog post to expound upon some of this. And I would like to release a toy demo, code demo of text generation in a simple domain, just to show how to get started with that if you're interested in playing around with it. So thanks. Any questions? Yeah. Yes.
The convolutional grounded truth. Do you see any? Do you have any instinct on why color bias?
Not really. I honestly.
Just your, if it's the fact that there's so many more shapes versus so many more colors.
Yeah, I mean, I think from the way they conducted the experiment that it shouldn't be that.
In theory, it'd be a lot easier to learn 9 things.
Yeah, yeah. I'm not actually as strong with CNNs as I am with RNNs, so I'm not sure that I could say what the cause of that is, if it's actually overrepresenting something. I'm also not convinced that, like as you say, that they eliminated every other possible.
If there was only 9 shapes and 9 colors, questions would it still have a 4 lines?
Yeah, well, I'm trying to recall actually for that. Did they? Sorry,
I didn't see it.
Yeah, I mean, I think they do control for that, right? Like on the right here.
In the middle.
Yeah, and it still happens, which is why they came to that conclusion. Yeah. Again, there are other possibilities probably, but it's interesting that it occurred. Yes. Oh, sure. Thanks for coming. For like what they did with entailment. Yeah. Yeah, I mean, I think for the most part, I see that as coming down to like novel ways to generate sentences. Again, I tend to think of this as by comparing it to like the paper out of Carnegie Mellon, like I think it was called Toward Controllable Text Generation, where they were using conditional autoencoders. But there would be a lot of value in being able to take an input sentence and then transform that. So the class, I don't know about data set, but like classifier you would use for that would, in that case would be like sentiment or tense, like I mentioned. But because those aren't really using similarity metrics like CIDR and things like that, they're just classifiers. You could really apply those to new data. It's conceivable. I'm not saying it would be stable, but if you were using an entailment classifier combined with those, then you could potentially train without any kind of predetermined data set, just using the classifiers to compute reward without a similarity measure. Does that make sense? Cool. Yes. Epsilon and greedy policy, I think, is more for value-based reinforcement learning if you're using like Q-learning. So, you know, they did that in the DQN paper from DeepMind, you know, their landmark paper that beat the state of the art in a lot of the target games. But they were using Q-learning, which is, you know, using action values at every given step. So with that, you actually need to use some method to encourage exploration. With policy gradient methods, that's not actually an issue because you're sampling from well, it's not as much of an issue. You're sampling from a distribution, so you get exploration by default. Yeah. Well, first of all, if you're experiencing any of the problems that I mentioned, like things like repeats, that would indicate the model hasn't learned something that you think it should have, like when to stop generating text. Any case where you think that, where it appears that agency, like having the ability to only get a positive reward if it's actually done the right thing, not because the ground truth sentence just ran out and so we stop training and we do, you know, cross entropy and back propagate the error. Any case where that would be helpful. Yeah, I'm not sure if I have an example off the top of my head, sorry. Yes? Okay. Okay. Yeah.
This is obviously
yep. For like the OpenAI paper on pre-training transformer networks. Maybe there's a different one. Okay, then I have not seen them.
There are so many.
Okay.
But there's okay. But you have the same one. It seems like every time right? And so wondering, are all these files good, or are there actually and I think that's the same question, but that's what trying to look at the person where you just bi-directional students. How big do you decide?
Well, I mean, you can use those together for sure. I mean, the bidirectional LSTM is, well, yeah. Yeah, okay. Maybe not bidirectional, I didn't think about that. But yeah, I mean, in the case of I guess that sounds a little open-ended, trying to compare all of these different models. I'm not really familiar with the one that you mentioned, or yeah. There you go. Just gotta wait for the right guy. Oh yeah, yeah. That's the original Transformer paper, right? Yeah. OpenAI just put out a paper a few months ago on pre-training the Transformer model on basically for a language model, and showed that if you fine-tune that on other more specialized tasks, that fine-tuning really reduces the training time. So yeah, that's what I thought you were talking about. Sorry. Okay. Silly me. Cool. Yes.
So you mentioned that reinforcement learning will solve some of the problems supervised learning. I'm wondering how much longer will this take to train the network?
Yeah, that's a good question. Not all these papers actually give their training time, but I would say if you were using just reinforcement learning without rather than fine-tuning on using it to fine-tune on something already trained with supervised learning, it's probably going to take more compute because of the sample complexity issue that I mentioned. But they haven't given exact numbers to that, so I'm not sure. I will say one advantage, though, to the RL method is even if it takes a little more computing power, it can generally be scaled out using something like asynchronous actor-critic methods. And it really is just compute. You typically don't face the same issues of overfitting that you do with supervised learning. It would be nice if it worked well enough to get that problem. But so you can kind of just let it churn if you have the computing power anyway. Yeah. Yes. Well, this would be deep reinforcement there. Yeah, I mean, I guess I didn't as explicitly state it, but everywhere. But throughout all of these, we're definitely using deep neural networks and then training them through reinforcement learning. Cool. Yes, one more.
There's a question about like the evaluation metrics, like when you train the reinforcement learning and reward with respect to score. It seems like in the end, what you the way you evaluate is you look at the test data and you look at your human knowledge and you say, okay, this is close to, but there is no real evaluation metric that you've optimized because you've trained on like trying to optimize the blue score, but then on the other new samples, it's very likely that they'll be very different. I mean, are there other ways to evaluate this than just by looking at the samples?
Sure, that's a good question. So first of all, I guess I would say if we find a weakness, the nice thing about doing it this way is if we find a weakness in, say, the blue score, then we can just make that better, actually. And we see that in cases like the CIDR score or metric, where they have a different version of it called CIDR-D that's actually intended to prevent gaming. So it has explicit calculations to prevent repeats and things like that, or any cheating that a model might do to try to get a higher CIDR score. So I would say the nice thing about going like straight for these evaluation metrics is that we can just, if they're not good enough, then first of all, we probably shouldn't have been evaluating on them in the first place. And second, let's make them better. But I mean, in the end, it all comes down to human evaluation, right? And so ultimately, what we'd like to see is reinforcement learning methods with better guarantees on the sample complexity. There are definitely researchers working on that, but if we could get the sampling complexity low enough, then we could actually interact with humans, have models that interact with humans and learn quickly enough to do that. I think things like pre-training the transformer model, formal language model, things like that help us get there because we have models that can learn on much fewer examples already. But yeah. Ultimately, I think that's what we're aiming for. Cool. Well, thanks, everyone.
Thank you so much, Andy. Everybody, we do have some sandwiches and drinks at the back, so feel free to help yourself. And Andy will be around for questions. I hope to see you guys in September. Thanks.